Hello, I am Paolo Dell Aversana. I'm Senior Geophysicist at NESPA Upstream and Technical Services. And today I'm going to talk about integrated geophysics and new methods for multimodal data analysis. This is the outline and the conceptual scheme of my lecture. I will introduce the concept of expanded integration that includes at least 4 different types of integration: multiphysics, multiscale, multi-domain, and multisensory integration. Expanded integration allows performing multimodal data analysis using new interpretation technologies with the support of new different types of sciences, including neurosciences, machine learning, digital sound processing tools, and so on. There are several new technologies that I'm going to talk about, like optimized visualization systems, audiovisual display, multimodal classification, and quantitative integration systems. So geoscientists every day combine information at many different spatial and temporal scales belonging to different physical and conceptual domains and coming from multiple geophysical methods. So basically we have heterogeneous information streams coming into the system. The system can be an individual brain, so an individual researcher, for instance, but more commonly it is a team or a wide organization. And what we try to do is to transform these heterogeneous information streams into coherent Earth models, where information is properly linked, properly organized. For instance, we use rock physics for linking different types of information. So let me introduce the concept of expanded integration. When we try to build a coherent Earth model, basically we perform many different types of integration. Multiphysics combination of different types of data like seismic data, gravity, electromagnetic data, and so on. But also we try to put together information at different spatial and temporal scales, ranging from well-logged scale up to regional seismic data. Moreover, we try to represent our information in multiple domains, like in time domain, in depth domain, in frequency domain, and so on. Over the past few years, I introduced also another type of integration, that is multisensory integration, where I try to combine images and sounds extracted from geophysical data. So let me start with the multiphysics integration. Why it is important? It is important because a geological model is generally more robust and reliable if it is constrained by many different types of physical parameters like elastic properties, electromagnetic properties, density, porosity, and so on. In general, a multiphysical model can be defined as a multiparametric model that is derived from complementary information, where every single cell is populated by multiple physical properties like seismic velocities, electrical resistivity, density, and so on. This is an example of multiphysics integrated model provided by courtesy of Daniele Colombo, where we can see a couple of seismic rock sections extracted from a big 3D seismic cube. And these seismic data were populated by 3 different physical parameters: seismic velocity in the upper right panel, then we have density and resistivity. So you can understand that every single physical parameter contributes in building a multiphysics model that allows us improving our interpretation of the seismic data. Of course, we can integrate geophysical domains like seismic and non-seismic data because these different physical responses are linked with each other. First of all, they are linked at a geophysical level. In fact, seismic velocities, bulk conductivities, densities, and so on are absolutely correlated with each other. For example, you can see in this composite well log where the density log, the resistivity log, and sonic logs are very well correlated versus depth. Moreover, the different geophysical domains are linked also at a deeper level, I would say at a petrophysical level. In fact, elastic properties electric properties and density properties have a common bridge linking them that we call rock cross properties. They are, for instance, porosity, fluid saturation, permeability, clay content, and so on. Moreover, geophysical and rock physical parameters are linked. In this example, we can see that the resistivity on the vertical axis is very well correlated with water saturation. So there is a strong link between resistivity and fluid saturation. So all these links allows us to perform an integration at a physical level, geophysical level, and rock physical level between seismic and non-seismic responses. There are many methods for integrating different types of geophysical data and for obtaining a multi-physics model. Probably the most sophisticated one is simultaneous joint inversion, where we have a multi-data vector in input. For example, this can be a vector consisting of seismic travel times plus Bouguer anomalies plus electromagnetic fields. We put all this data simultaneously in the system, and then we try to minimize iteratively a joint objective functional. And when we are happy about the level of minimization of this joint objective functional, we exit from the loop and we get a multi-physics model. Now let me talk a little bit about multi-scale integration. Geoscientists, engineers, managers, everybody needs information at many different spatial and temporal scales with the objective of minimizing uncertainties and overall for taking robust decisions. There are many different methods in geosciences, and each method provides data with a spatial scale that can be completely different from other methods. So we have to deal with the spatial scales ranging within many orders of magnitudes. Why multi-scale integration is important? The first reason is because natural systems show a hierarchical organization, let's say a sort of fractal organization, and all spatial and temporal scales are equally important in order to understand how our system works. On the other side, human brain and cognition have a similar hierarchical fractal organization. So technology should be optimized, taking into account both hierarchical and fractal architectures, I mean of nature and of the brain. There are several methods for performing this type of multi-scale integration. Again, one of the most sophisticated one is constrained joint inversion. For instance, we can use well logs for constraining simultaneous joint inversion. Another type of integration is multi-domain integration. Basically, geoscientists try to combine and to analyze data in multiple domains, let's say in time, in depth, in frequency domain. This is very important because analyzing information simultaneously in many different domains allows to understand the data much better. For example, in this figure, we have a seismic trace. From this seismic trace, we obtained the spectrogram using the Stockwell transform. Of course, we can use also other mathematical transforms. In this case, we have the S spectrogram of a seismic trace. And we can see that it is very important to have at the same time the same information in terms of time series, a seismic trace, and spectrogram in terms of frequencies and amplitudes. Of course, the same thing is valid also for different data, like resistivity logs. In this example, we have a resistivity log versus depth and its spectrogram, or for gamma ray logs. In any case, it is very important to have a multiple domain representation of the same information in time or in depth and in frequency. This is what I mean by multiple domain, multi-domain integration. Finally, the fourth very important type of integration that I have been trying to introduce over the past few years is multisensory integration. What I mean by that? I mean that we commonly use images for interpreting our geophysical data, but we can also extract sounds from our geophysical data. And it is very important to have a simultaneous representation of images and sounds coming from the same geophysical object. The reason is because our brain evolved for integrating multisensory inputs. In fact, analyzing information at the same time with different sensory modalities allows deep data cognition. And geophysical data analysis should take into account also this very important basic cognitive feature. How do we extract sounds from the spectrograms? Basically, we transform the physical quantities like seismic data, for instance, or electromagnetic data too, into spectrograms, and then we have frequency and amplitudes versus time, and we can transform this quantity into MIDI attributes like pitch, sound intensity, note duration, and so on. MIDI is a typical standard protocol that we use in digital music, and it means musical instrument digital interface. There is a very simple non-linear mathematical relationship between instantaneous frequency and the MIDI note number, and using this relationship we can transform every single point of our spectrograms into musical notes, into sounds. In such a way we have, for instance, a seismic trace on the top panel on the right, the spectrogram, for instance the Stockwell spectrogram in the middle panel, and a MIDI file in the bottom panel. MIDI file means that we can listen to it. So at the same time we have a multiple representation of the same data in terms of time series, frequency content, and also a double perception of the same data in terms of visual representation and audio representation of the data. This is what I mean by multisensory integration. And we can do that trace by trace for big seismic sections or for big 3D seismic data. Basically, we trace by trace can have the seismic information in the traditional way, so we have the seismic trace, but also we can have the MIDI representation, so the audio representation of the same seismic information and its spectrogram. So this is a multi-modal, multi-domain, I would say a multi-sensory representation, integration of geophysical data. Examples of this type of audiovisual display can be found on the web very easily. Now, after talking about expanded integration, let me introduce the concept of brain-based technologies. So the basic concepts of expanded integration drive directly to the development of new algorithms, new methods, new technologies that I call the brain-based technologies, simply because they are based on a sort of ergonomic principle of the mind. Technology works better if it takes into account the features and the limitations of human cognition. So using this concept, I try to bridge the gap between geosciences and neurosciences. The main cognitive features of human brain are, first of all, integration, and I would say expanded integration. Our brains everyday works for combining information at many different levels. Another very important cognitive feature is imaging, then mapping, combination of multisensory inputs, pattern recognition, and so on. Examples of brain-based technologies are optimized visualization systems that are based on human visual perception, and several people are working on this concept, trying to develop new technologies taking into account the functioning of human visual perception. Audiovisual display is another example of brain-based technology where we try to perform interactive analysis of multisensory information, audio and visual. Another technology is MIDI and audio sound pattern recognition for seismic data clustering and classification, and I'm working on this concept. Machine learning and neural networks for seismic phases classification is another very important brain-based technology, especially when it involves also MIDI files. And finally, quantitative integration systems represent probably the most important example of brain-based technologies, because in this type of software platforms we combine multidisciplinary data trying to obtain multi-physics and multi-parametric geophysical models. So let me say just a few words about quantitative integration systems. They are much more than computer platforms. They are a sort of collaborative environment involving brain-based technologies with the objective to combine multi-physics, multi-scale, multi-domain, and multi-sensory information, getting the concept of expanded integration. Examples of algorithms that we implement into quantitative integration systems are Bayesian joint inversion of multi-physics data, automatic classification using audio-visual multi-attributes, advanced visualization tools, audio-video displays, and so on. This is a schematic structure of a typical quantitative integration system. So basically we have multidisciplinary data in input, plus some a priori information. Then we have a library of relationships. This can be rock physics relationships for linking, for instance, seismic with electromagnetic data, with gravity data, and so on. But in this library of relationships, we also have the mathematical formulas for linking the spectrograms with the MIDI file, for getting sounds from seismic data, from electromagnetic data. Then we start from an initial multidisciplinary Earth model, and we use iteratively many different integration tools and algorithms like constrained inversion, cooperative inversion, Bayesian simultaneous joint inversion, and so on, supported by advanced visualization tools, geostatistical modules, and so on. And finally, the final output will be an updated multidisciplinary Earth model. So this is just the general structure of the quantitative integration system that represent probably the best realization of the concept of expanded integration. So let me conclude. I introduced in this lecture the very important concept of expanded integration. It is a combination of different types of integration, like multi-physics integration, multi-domain integration, and multi-sensory and multi-scale integration. This type of expanded integration is supported by brain-based technologies that are based on a very important principle. Computation technology works better if its architecture is designed consistently with the human cognitive abilities and limitations. Examples of brain-based technologies are optimized visualization systems, multi-domain and multi-sensory interpretation methods, multi-modal automatic classification approaches based on machine learning, and so forth. Quantitative integration systems probably represent comprehensive and collaborative, I would say the most comprehensive example of brain-based technology. They are collaborative environments that are addressed to expanded integration. So here I report several fundamental references where you can find all the details about the concepts that I explained during this lecture. And also I wrote a couple of books linking the concept of integration in geophysics with cognition, and they were published by EAGE publication. Finally, I'm going to print a new book that will be officially published after summer, where I explain in detail the concept of expanded integration and how it is combined with geocognition and brain-based technologies. Thank you.